Okay, so let's talk about, can you all see the slides? Can you all see the PowerPoint slide? Okay. So last week we already talked about SOP, POS, all right? Okay. Now we talk about the mean and the max term. So in the mean term, for three variables, let's say F equals to A, B, C plus, this is the mean term. Okay, mean term. All right, the max term will look like this. Okay, so the max term, you see all the zero, then it look like this. Let's say there's no such this mean term. Let's say this one don't have. This is zero. And the max term, let's say this is the mean term. So the max term will look like this. That's how the max term will look like. Okay, so this is the mean term and the max term. All the variable must be clearly specified. All right, all the variable must be there. So the mean term and the max term. Okay. The next thing is Karnaugh Map. We need to Karnaugh Map allow us to do simplification. So you have a systematic way of simplifying Boolean expression, minimize the number of logic gates required. You present all the possible input value. So you have 4 variables, you have 2 variables, then you have 3 variables, you use 2 times 4 or 4 times 2. Then you also have 4 times 4 K-map, 4 variable. Then you also have 5 variable, 8 times 4 map. So, or you can also say this is a 3-dimensional map. Okay. So this one will not be tested. Because due to our limit of our visualization, you can only do up to 5 variables. Anything more than 5, there's another method. I think clean Mesklarsky method. Right? This one will not be taught, but then if you want to look it up, you can. Right? Before you understand Karnaugh Map, you should understand there's what you call a gray code. At one time, only 1 bit change is possible. Right? At one time, you only change 1 bit, and you must cover all the possible scenario. So for 1 variable, it's either 0 or 1. For 2 variable, from 0, 0, it go to 0, 1. Then it goes to 1, 1. Then it goes to 1, 0. Okay? So there's in 3 to 5 variables, you can refer it to the Karnaugh Map. Okay? So this is how it looks like. It's very confusing. The arrow show that the changes of the scenario, all right, which bit got changed and so on. Okay, each changes, each box, okay, from this box to this box, any neighboring box, there's only 1 bit change, all right? There's only 1 bit change to any neighboring box. Okay. All right, so this is how it looks like. So I prefer you use in this form, A bar A, B bar B, all right? So this A bar, B bar, A bar B, A B bar, and A B, all right? This is 2 times 2, K-map. Let's say you have a function y with this formula. So you can see the truth table. From the truth table and the K-map, it looks like this. It's 1-to-1 correspondent. Okay. Okay. This one is 2 times 4 times 2 K-map. All right. This is the 1-to-1 correspondent. Okay. All right. Remember that the last line is not here, it's here. Okay, so from here, from the sum of product expression, you can get this one. This is the K map. So from the K map itself, this one is a 4 variable, okay, and you can get the K map from here. All right, the Karnaugh map is here. Okay, this is how the Karnaugh map will look like. So this sum of product expression over here, then you know which one is 1, so you can put it in. Okay, and this is the function, output function y. Okay, there's another way to represent it, but then this, you can see this is W. Okay, this portion is W, this portion is X, all right? This whole portion is X, this whole portion is W, this whole portion is Y, this whole portion is Z, okay? Same like A, B, C, D, okay? Or maybe you can do an insert sheet. Okay, so this is X, W is here. You can see, this all W. And insert sheet. X is here. These are X, okay? Right? Then Y. Then you can see Y is this one. This is all Y. Y. This portion is Y. Z. This is portion is Z. Okay? This is Z. Okay. So next. Okay? So you do the truth table, then from the truth table, you do the K map. Okay? So you have 2 pair, 4 pair, and 8. All right? So you try to circle either by 2, by 4, or by 8, depending on how is your size. Okay? This is how the K map looks like. Okay. Let's say if you have here. So from here, this is your truth table. Okay? It's your truth table. And you can see here. Oh. This one is wrong. Okay. 0, 1, 2, 3 until 15. Okay. So this one referring to 0, 1, 3, 2. 3, 2. I see CD. CD is here, number 3. Okay. 3, 2, 4, 5, 7, 6, 8, 9. You can see 8 is not here, it's here. And 15 is here. So you must remember the position. Don't get confused. Okay. It's not like this. This one is wrong. It's not like this. Not like this. Not sequentially. This one is wrong. Okay, this one is wrong. Okay, this one is wrong. Okay. Okay. So then from here, you're going to circle. Okay. You're going to circle the KMF. Okay. 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 Let's say you have a KMap and you have a F equals to 1. How are we going to draw the Karnaugh map? How are we going to put with F equals to 1? How do they provide? How do you know the zone? Okay, from here you can see how do you know the zone? So where is A? A bar, A, isn't it? AB. This whole line is AB. This whole line is AB bar. So, or from the truth table lah. From the truth table, it won't be easier. Okay, this is wrong, huh? Okay. So from here, yeah. Okay. Let's say you can see A is 1, huh? Let's say you have a function f equals to 1. So how are we going to enter if x equals to 1? If x is equals to 1, how are we going to enter? So all 1 lah. Okay? This and f equals to 1. Let's say f equals to a. Which part is it? When it's a. So a is when from 8 onwards, isn't it? 8 until 15, isn't it? So 8 until 15, this is a. You can see this a. So the rest is 0 lah. Okay? Let's say f equals to AB. Then is this one lah. AB, this section. Okay? So where is the section of C? The section of C is here. C section. So this is C. This is C. Okay? Where is D? D is this one. D is D here. So the intersection part will be this part will be CB lah. CB lah, the intersection part. Okay? 4 variable. Okay? So f equals to 1, then 16 boxes. F equals to 1 variable, 8 boxes. 2 variable, 4 boxes. 3 variable, 2 boxes. 1 variable, okay. 4 variable, 1 box. Okay. Clear? Clear? Any question? So this A, where is B? B is here. You can see this is B. This is B. This here is B. This is B. Hey, no. Delete. This is B. This is B. This part is B. Okay, this part is B. Okay, this part is B. A is the lower part. Okay. Now do you know which section is which section? Which part is A, B, C, and D? Clear? Clear. Okay. Okay. Just remember, you sometimes you make mistake. You can see 15 is here. Okay. 15 is here. It's not in the bottom. It's here. Okay. Right. So, all right. So let's say you have a Karnaugh map like this. Karnaugh map like this. So the first circle is AC. You can see this section is A. This section is C. So AC. Second circle is A bar B. This line and C and D. Okay. All right. Then this one is C. Second circle is this one, C bar. A bar, B bar, C bar. Here. Then the third line is A, B, C, D. A bar, B bar, A bar, B, D. All right. So this is a simplified solution using Karnaugh map. Okay. Because there's a limit to the simplification. If you circle wrongly, then it's less simplified, like this. Okay. But you like to circle what to do? Okay. So you must circle the biggest one first. Okay. All right. Any questions so far? The simplification process depends on you, whether you can simplify by drawing. Okay, you draw the largest circle first. Okay, it's the largest. Largest circle you try to draw first. So try to find box of 8, box of 4, box of 2. Okay. Any question? So far so good? Okay. Then the next thing is, okay, once you found it already, the F also can overlap. Okay, so F is BC, so this is BC. The top one is BC, bottom one is AC. So the boxes also can overlap. Let's say you don't know that it can overlap, so you do like this. So it is less simplified. Less simplified. Okay? So because you draw a smaller circle instead of bigger circle, you can draw the smaller circle. If you wrongly circle, the rest of the thing correct, but you wrongly circle, so your simplification will be less. Okay? All right. So these are the steps for Karnaugh map. Okay, you can read through it like Eng said. English, help yourself. Okay. Loop of 2 will eliminate one variable. Loop of 4 eliminate 2 variables. Loop of 8 eliminate 3 variables. Okay. These are some of the steps. Okay. 4 variable simplification method. Okay. So let's say if you have y equals to this one, so you use the SOP and draw the Karnaugh map. Then from the Karnaugh map, you try to circle and make the simplification circuit by using the circle. So by using the circle, you can see it's further simplified. Okay, there's also some circuit where you have a scenario called don't care. Don't care means that the input or the output, okay, certain combination of input, don't care whether the output is high or low. So don't care the input X in the looping process is needed. Okay. Certain input condition for which there are no specific output level. Okay. Usually because this input condition will never occur. Okay. It will never occur in the real life. Clear? Yeah. So let's say you have this scenario. You have X. X can be 0 or 1. So in this case, what will happen? You can circle like this. Instead of like this, okay, you can circle here so that it become 4. So it will be something like this. YZ plus W prime W bar Z, all right, something like this. So let's say you have a truth table. That truth table will say that when the elevator is not moving, okay, the door, whether the door is open or closed, it doesn't really matter, correct? Right? Doesn't really matter because the elevator is not moving, okay? So when the elevator is moving, all right, and is moving on certain condition, let's say it's on the top floor, okay, on the top floor, on the third, okay, top floor, doesn't really matter because when it's on the top floor, it can be open or closed because it's already on the top floor. Okay, so this is just an example. So you can see if it's don't care state, you can put X. So from here, you can see initial the truth table is like this. Then you try to change X to 1 or to 0, whichever is possible that help you to make a more simple circuit, simpler circuit. So you can see here, you circle 3 times, 4 times 3. Each circle got 4 boxes, so circle times 3. Okay? Then you get M equals to F1 plus F2 plus F3 like this. So M bar, F1, F1 over here, plus F2, F2 over here, and F3 over here. Okay. 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 When you say don't care, the condition you put here X is 0 or 1. Okay. So this is a problem 2, BCD circuit. So in a BCD circuit, so you can see the output from here. When the is 9 is okay. When after is 10, all the output will be either don't care, okay? In the don't care state, okay? Because this is a BCD, all right? BCD operation, okay? So this one, if like this, if you added the don't care state over here, you can further simplify the circuit. So this circuit is much easier than this circuit. Okay? So you can also map using POS, but POS is slightly more difficult, right? Because you need to think in a different way. Okay. So this is, you use POS, you see there's a 2 circle. You can see A. This is A, and this is B, over here is B bar plus C, all right? So this is B bar plus C. And if you see POS and SOP, it's actually the same thing. Universal circuit, I told you, it's a NAND, and any circuit you can use AND and OR, and not, okay, and set up truth table. So let's say you want to implement a NAND gate using inverter using a NAND gate. So you can do like this. If you have two NAND gate in serial, it can become a AND gate, all right? These two negate each other. If you have three NAND gate, you can become an OR gate. You have four NAND gate, you can become a exclusive NOR gate, all right? Exclusive. You have four NOR gates, you can use become a NAND gates, okay? Okay. The same thing goes to NOR gate. You can also do like this using a NOR gate. Okay. So whichever way you do, you can do it in NOR gate. Okay. So most of the chip, they are implemented using a NAND gates only. Okay. Only NAND gates. No AND, no OR, nothing. Only NAND gates. Okay. Right. Let me see whether got question or not. No. Huh? Okay. Then how do you design the circuit using only NAND gates? So you use the Morgan's theorem. Yeah. Oh, let's say if you have first example, let's say this is the circuit you got, right? And you got the Boolean expression. So first you change G1 to become a not AND gate. So here you have a not AND gate, isn't it? Then you have these two bubbles that cancel out each other. So in the end, you get a AB plus CD, okay? Which is this one. Easier to comprehend. Okay, the next one, example, you have a circle like this, a circuit like this. So you change this to a not AND gate, right? Not OR gate. Then this is bubble, isn't it? Go and click like this. Then these two bubbles will cancel off each other. Okay. Then over here, you have a bubble. This one will cancel off each other. And you add another NAND gate to it. Then it become a inverter. Okay. So you can also see from here, these two example, a NOR gate. So you change the not AND gate, not OR gate to a NAND gate, to a not AND gate. So these two bubbles cancel. Then you can derive the solution. Okay. The same thing goes to here. You just basically change the NOR gate to a not AND gate lah, or NAND gate to a not OR gate lah. And then you remove the bubble along the way. You can do the simplification already. Okay. Any question so far? So far, so good? So far, so good? Okay. Okay. So now the next thing is okay. All right. So let's do the question, tutorial question. Tutorial question number 5. Okay. Okay. Can you all see the document? Word document? Can you all see or not? Can see or not? Please respond. Okay. So now this is the question. Part A only I do for you. So let's insert a table. Before we insert a table. Okay. Insert a table here. So 4. 6. 20. Okay. So initially here you have A, B, C. Okay, A, B, C only. So I have 1, 1, 0. And here you have 1, 0, 0, 1. Here you have 1, 1, 0, 1. Then here you have 1, 1. Input sequence. Sequence A, sequence B, sequence C. Oh, sorry. Like this. Sequence A is sequence A, sequence B, and then this is sequence C. Sequence A is 1, 0, 0, 1. Sequence B is 1, 1, 0, 1. Sequence C is 0, 1, 1, 1. Okay, and the output is what? The output will be 1. Oh, sorry. Wrong again. So A. And here is B. And the C. So the output, let's say F. So what is this? 110 equals to 6. 011 equals to 3. 001 to 1. 111 equals to 7. Okay, then we're going to do some reorganization. Reorganize the truth table. A, B, C, and F. And here we have 0, 1, 2, 3, 4, 5. Okay. So when it's 1, 0, 0, 1, this one is 1. When it's 3, it's 1. Okay. When it's 6, it's 1. Okay. So when it's 7, it is 0. So the rest is X. Okay. Okay. So now we got this one already. We got the truth table already. Then let's build the Karnaugh map. You have to build the Karnaugh map. So build the Karnaugh map. Okay. So insert table. Let's see. So this is A bar. B bar, C bar, B bar, C, B, C, B, B bar. Okay, so from here, the Karnaugh map, you have the function. This one, A7 is equal to 0. So it's 0. 1 equals to 1 equals to 1. 3 is equals to 1. And the rest of, and this one is 6, where is 6? 6 equals to 1. And the rest all equals to X. Right? The rest all equals to X. So then you can find F equals to what? Draw a circle. This circle is over here, one circle. Okay. Then over here, another one circle. Okay, one circle. F equals to B bar. And there's also another circle. Oh, not like this. Another circle. Like this. Okay. So this circle means is what? Is this circle is C bar. Then you plus another circle, which is A bar. There's the A bar. Update. Okay. This is the A bar circle. Okay. So this is the function. Then you can draw the circuit lah. Okay. Any question so far? No, huh? Okay. So now we're going to go to tutorial 2, lecture 3. Lecture 3, yeah. All removed already. Okay, lecture 3. All right, I'm going to share you the PowerPoint. Can you see the PowerPoint? Can you see the PowerPoint? And you all see the PowerPoint? Okay, so let's get started. So we're going to talk about how we design a half adder, full adder, and then we do a parallel adder and BCD subtraction, addition and subtraction. Then we go to a decoder, the encoder, decoder, encoder, multiplexer, and demultiplexer. Okay, demultiplexer. So first you have a combinatory circuit. So you have the input and the output. Okay, and you define it by Boolean expression. One of that is a half adder and also a full adder. And you can design various ways. You can design the half adder and or gates, XOR, AND gate, Nand gate, and NOR gate. All right, so this is the truth table for half adder. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, but the carry bit is 1. All right, so this is just a half adder. Okay, not a full one. This is how you implement using AND and OR gate. You also can implement using a XOR OR gate. Okay, XOR and the AND gate. So this is much more easy to understand. Half adder. All right, so far so good. Then this is how you use using a NAND gate, and this is how you use using a NOR gate. Okay. Okay. Then you can design a full adder using a half adder. You can use this. You got 3 input. Okay. So S is equals to 1 when only one input is 1, or when all the 3 input equals to 1. The output S odd function can be implemented with 3 XOR gate. The output of carry C has a carry of 1 if there's 2 or 3 input equals to 1. All right. So this is how the truth table, you have an input. So Z is the carry in. All right. So if all 3 is 1, then you have the output, which is 3. The sum of 1, carry is 1. Okay. So this is the function for the full adder. Okay. There's 2 functions. One is the sum. Another one is the carry function. So you can see the sum function is distributed all over. So you can never able to draw circle. So the only circle you can draw is the smallest circle. Okay? Something like this. You can only draw the smallest circle like this. Okay, and draw 4 of them. So is that the case? That's the best to use the XOR gate. This for the carry, this is how it looks like. This is the full adder. This is the circuit using N, or you can also use 2 half adder, which is much more much easier to understand. You just use a half adder, right? The input and the carry in will put into here, okay? And here, okay? So you get the same output. You connect 2 half adder together. The output of one of the sum, you put into the input of the sum. The output of the carry, you put it into a AND gate, and then the other input, you put it inside the adder, okay? So basically, you have a half adder. You're going to make from a half adder, you can make a full adder. From a full adder, you can make a multi-bit adder. You just build the circuit on top of each other. Chain them together. Okay. This is how you use a full adder using a half adder. This is how the full adder is implemented, only using NAND gate. And this one is for NOR gate. You can do parallel bit adder, right? Like this. So there's all these 2 bits is added together. You got 3 full adder and 1 half adder. So the first half adder add together, carry will go to the second full adder. Okay, carry will be carry forward. Okay. Any questions so far? So far, so good. Okay. So okay, so this is how the 4-bit binary adder is done. You can also do a subtractor, right, by adding an XOR gate to it, and it will subtract. Okay. So you can see here there's an input. If it's 1, it's subtract. If it's 0, it will add. Okay. So this is a 4-bit adder and subtractor. Okay, then you have a BCD addition. So in BCD addition, BCD basically you call it a binary coded decimal. Okay. So it's used in calculator, cash register machine, all right? Anything that has digital display, but you want to display up to 9, not 10, 0 until 9. So if the sum greater than 9, or if the carry is out, then the 4-bit group is generated. It's an invalid result. So you need to add 6 to the sum, all right, total sum. If the sum is order, okay, in order to skip the invalid state, okay? So if the result within result when 6 is added, so you simply carry to the next 4-bit. Okay. So this is how it works. Okay, in the BCD addition. Okay. So if the output, if the F output is more than 9, or the carry bit is set, then you add 6 to the output. Okay. So this is a BCD addition. Then you have gates like a decoder and encoder. In a decoder, basically it's like this. You have 2 input line and 4 output line. So these 2 input line, from these 2 input, okay, 0, okay, you have 0 until 3. So the input is 0, you select line 0. If input is 1, you select line 1 and so on, okay? There will be 4 output line, right? So if active high, only 1 output will be high. If active low, only one output will be low. The chipset will be the chips that is used will be this one, 74138, 74139. Okay, that's the chipset that used for the decoder. Any question about the decoder? All right, in a decoder, all the output is the same except the one that has been selected. Okay, so if it's a active high, the selected output will be 1. The rest of the line will be 0 watt. Okay, clear? Okay, any questions so far? No, that is the decoder. So you have 1 to 2, 3 to 8 line decoder. Okay, you can also chain that together. You can do 2 to 4 decoder become a 3. You can build this one, 3 to 8 line decoder can be built using a 2 to 4 line decoder. All right, 2 unit of 2 to 4 line decoder. All right, you can build that. Okay. Okay. A decoder is a combinatory circuit that accepts several input that's correspondent to a binary number. So you can see, you put in a binary number, you select the output. The output is activate only the output that corresponding to input. Okay. So the decoder can constructed as a combinatory circuit that converts binary info into unique line output. Okay. So normally you have n input, then you have 2 to the power n minus 1 output. 2 to the power n output, not minus 1. So this 1 to 2 line decoder, 2 to 4 line decoder, you can see from here, these are all possible scenario for 4 line decoder. Okay. Then you can have an active high or active low. If it's active low, that means that the output will be low, the rest will be high. Okay, so this is using the Nand gate. If you use active high, then you use the AND gate. So all the output, one output will be high, the one that you select, the rest will be low. So this is a decoder. Okay. Okay. So this is the truth table for the 2 to 4 line decoder. Then you also have the input. You can see this is the input, 3 to 8 line decoder. This is the input, and this is the output. You can see one straight slanting line. Okay. All right. So if you choose 3, so D3 will be output to 1. Okay. It's also referred to 1 of 8 decoder because only one out of 8 output is activated at one time. Okay. So this decoder. So you can see you can make a 4 to 16 line decoder by using a 2, 3 to 8 line decoder. So this kind of construction you can build on top of each other. Okay. Logic gate. All right. You can also implement a logic gate using a decoder. Okay, using a decoder, you can build a logic gate. So this one is you use a full adder. All right, we develop a full adder using a decoder. You also can, because the decoder you can have all the output in it. So this is something similar to truth table already. Okay, something similar to truth table. Okay, then you have the encoder. So encoder is the opposite of decoder. Only one of the input is different, active high. All right. Only one of the input, if it's active high, only one of the input is 1, the rest is 0. You have an 8 input. If line 7 is high, then the output will be A equals to 1, B equals to 1, C equals to 1. If it's active low, then it's the opposite. All the input line are high, only one output line is low. All right. So you have here M input, so only one high at the one time, and M bits. All right. Coded down with M bits. So you can see here 2 to the power M. So from here you can see here might be 8 inputs and okay, 8 inputs and here will be 3 output. So far so good. So far so good. Anything? Quiet? Okay. Okay, clear. All clear. Okay. Right. So there is the encoder. Right. Then you also have priority encoder lah. Okay, you can put a priority function. Then you have a multiplexer. Multiplexer is 2 to 1 line, 4 to 1 line multiplexer. So multiplexer, all right, is something like a decoder and a select. So you have the input line. So this input line not necessary or not necessarily only one active, all right? Okay, it can be anything. The input lines data stream can be data stream, can be anything. Okay, can be anything. This is the input, data input over here. Then the select input is that which line you want to select. Okay. Okay. Suppose you select line 0, then whatever data from line 0 will get channeled to output Z. So output Z will select line 0. So this is a multiplexer. So you can see here, there's one arrow, all right? You can interchange whichever one you have. So there is a multiplexer. Okay. So this is used in phone line or telephony and so on. All right. So you have 2 to 1 multiplexer. This is the logic function, and you also have the truth table. Okay, this is a 4 to 1 line multiplexer. Okay, this is Z. Okay, so you can see this is the input, this is the output. You select which input line you want. Okay, to select from. Okay, this is how you should draw the multiplexer. Okay, and you can see from the timing diagram how does the multiplexer work. Okay, and the multiplexer, you have the input Okay, now you have the input. It's the opposite of a multiplexer. Okay, so you have the input, then you select the input line. From here, the input, you want to select the output actually. You want to select the output line. Okay, so that is the multiplexer. Okay, which you want to select the output. Let's say you select line O1, so the our input data here will be channeled to O1. Okay, so that is a demultiplexer. Okay. Right. Then you have comparator. Comparator. Okay, we continue another day. Okay. So I finish all. You go back and you do tutorial 2, including question 5. You submit. Anything else before we close shop? Anything else? Any question? So I stop the recording first before getting too big.
Sir,